How about now? Can you hear me? Okay, we're online? Or okay, that's good, thanks. Mm-hmm. Oh. Good. Okay, let's get started. Now we're into the last 5 lectures of the semester, and we're going to go deeper into memory today, which is, as you learned from the last lecture, one of the most critical components. You can hear me? Or is it good now? How about now? This is on, it's green. Okay. How about now? Better? Yeah, I'll use the other one. Online was good? Okay. If you don't have robustness, then you don't have computing. Let's see. Is this better? All good? Okay, I don't know what the problem is. Is it online good? Online is good, so I don't know what's the issue over there, but this is green. And I don't know. Oh, is this muted? Oh, okay, how about now? Somehow it was muted. Okay, there you go. So this is what we call a user error. I should have checked the mute button over here. All good, all right, okay. Okay, so it's not the fault of the hardware, it's fault of the user in this case. And a lot of computing errors are actually user errors. There have been a lot of studies that are made, and users are the ones who make the most mistakes. But then software bugs and also hardware bugs are also quite substantial later on. User errors are a bit easier to fix. Okay, so we're going to talk about memory. And my hope is we'll at least cover the basics of caches today. But just a reminder, you have an opportunity for another 1% extra credit by reviewing Amdahl's seminal paper. And these are some of the readings. So if you want to supplement what we're talking about, please, especially do the chapter that we wrote with my PhD student about 11 years ago. It's really a nice introduction for a layman, actually, for memory systems. Okay, last time we covered memory is critical for computing, and we discussed many different metrics that memory design affects. We talked about some memory fundamentals, which I'm not going to talk about again. We're talking about memory organization and technology, and I'm going to go through some slides again to jog your memory. And this was a hierarchical memory structure that we looked at, especially in the DRAM subsystem. I'm going to talk a lot about DRAM subsystem today, and then we're going to talk about other things too. But if you recall, you have a memory controller, and then it's connected via some buses channel to many memory modules, and each memory module has memory chips, and each chip internally has a bunch of arrays called banks, and each bank consists of a two-dimensional array of cells. But then we're going to break this also down in a little bit, so we're going to really understand the lower level operation of this as well. And we looked at the DRAM subsystem organization from the top down. I'll go through these slides relatively quickly because we covered them again. These are the channels connected to a real processor. You can see 4 modules here, or dual inline memory modules. And each module has a front and a back in this particular case. And these are called ranks. Basically, it's a collection of 8 chips in this case. It could be 4, it could be 16, it could be 32, depending on the chips. And then these ranks share address and command buses and data buses, as you can see. So you can access only one rank at a time, at a given time, and part of one of the bits in the address. If you have 2 ranks, one bit needs to determine which rank you're accessing. So basically mapping the data to the appropriate rank becomes an issue, and we'll talk about that in a little bit. But essentially, physical address, part of the physical address is used, it's called chip select, let's say, in old terminology, but it's called rank select, and this, you're really selecting one of the ranks using one bit of the address. And then you access the data, you get 64 bits from a rank, and there's a multiplexer, as you can see, depending on which rank you're accessing. This multiplexer is also controlled by the rank select signal over here, and then you pick the data that you're accessing, and then send it to the processor. Okay, that's how you access 64 bytes. We're going to see a little bit more of that also. And then we broke down the rank. Each rank consists of 8 chips, and each of the chips supply 8 of these bits, so that you get a wide supply of data. Even though each chip supplies a smaller piece of the data, 8 bits, for cost reasons, because if each chip was supplying a larger amount of data, there would be more pins in the DRAM chip, so the cost would be much higher. This way, we have lower cost chips, but then we can aggregate them together so that we can actually get higher bandwidth, let's say higher data throughput, by accessing all of the chips concurrently at the same time, right? That's the idea over here. That's why it's called a rank. It's kind of like a rank of soldiers. All of these chips receive the same command, same address, same row, etc., except they provide different data, right? So they do the same thing, but provide different data in this particular case. Okay, and then if you look at a chip, it consists of 8 banks, and you've seen banks before. Banks, there was a good reason for having banks, which is if you didn't have a bank, if you didn't partition the data array into banks, then you would have a single monolithic array, given the same size, total size. And single monolithic array would be very long latency because of the interconnects and the row decoder, et cetera, that you need to build, and the multiplexer. In this case, you partitioned it to 8 banks, and this way, each bank can be lower latency, and you can also exploit the parallelism or concurrency across banks by starting multiple accesses across different banks, either in the same cycle or across different cycles. In this particular case, we're looking at DRAM. So DRAM is very cost sensitive. So starting accesses concurrently across all banks requires you to send an address to each bank and a command to each bank, which is really expensive. So if you want to send an address and a command to each bank, you need to actually have pins to support 8 concurrent addresses and 8 concurrent commands to be sent to each bank. That's expensive. So normally, DRAM chips are built by sending one address and one command to a particular bank at a given time. Then you start access to that bank. And then in the next cycle, next clock cycle, you can send the other address to another bank. This way, you don't need to support more address and command pins than needed for one bank. So I'm giving you the design choices that are actually there. Many of them are dictated by cost, as you can see. But you still get some pipelining benefit because of you can access banks concurrently after you start the accesses. And you've seen this before. We've seen this in vector processing, as early as vector processing. But now we're looking inside the chip. We're going to look a little bit more inside the chip before we move on to other things. Okay, once you break down the bank, it's a two-dimensional array structure. And essentially, you see a two-dimensional array of cells. Each of these over here is a cell. It's not to scale because you can see that on the you have 32,000 rows in this particular case, and 2 kilobytes of columns, which is 16,000 if you think about it. And one column can be thought of as 1 byte, essentially. So when you access DRAM, there's something called a row buffer. We're going to talk a little bit more about that. It's really a row of sense amplifiers. That's how you sense the data. And data needs to come to the row buffer first when you access a row. And then you access different bytes in the row. So if you want to access 1 byte, for example, you bring in the entire 2 kilobytes of row into the row buffer, sense them, and then you multiplex using this multiplexer, which you know very well about, multiplex 1 byte out of that row buffer. That's how you get a single byte out of a bank. And you get different bytes across different banks in different cycles, as you can see. And that multiplexer helps you select which bank you're accessing. Okay, this is where we stopped, actually. I kind of spent a little bit more time than expected to talk about this because we're going to build up using this. But even this is an abstraction. So we're going to break down this row buffer into smaller, let's say, arrays, because building this 32,000 by 16,000 bit cell array is possible. But if you build it, it's long latency because you have a large decoder, you have large interconnects, and that increases the latency, RC delay. And also reliability is hard to maintain if you have very large arrays. It's easier to build large arrays at low latency as well as high reliability. So we're going to break it down. But before we break it down, this is the abstraction normally what a memory controller sees. So how does this thing operate? So assume that we have these columns and rows. When the memory controller needs to access a bank, I already said this actually, internally a bank consists of many cells and other structures that enable access to cells. I'm going to go internally a little bit more. But basically, when you want to access a bank, you first need to bring the row that you're accessing. So you need to supply 2 addresses, row address and column address, which is part of your physical address. After you supply the row address, the data needs to be sensed using sense amplifiers. The sense amplifiers are also called a row buffer. We're going to see this a little bit more in detail, how this is built. It's actually built using SRAM-like cells, cross-coupled inverters. Initially, you have nothing to sense. You didn't access this array. Now, if the memory controller wants to access row 0, column 0, what it does is it sends the row address 0, which gets decoded using a row decoder, which is the same as the decoder that you've seen in the past. And this row decoder enables a word line of row 0. All of the cells in that word line get connected to their respective bit lines or columns. And the row buffer, the sense amplifier, sends the data in those cells and then basically captures the data in the row buffer. Now we've captured the data. We're going to see this a little bit more. Now you have the entire 2 kilobytes. Let's say that row was 2 kilobytes as consistent with the previous picture. Now the memory controller sends the column address. And let's say we want to read column 0. We want to read the data at column 0. Let's say that's an 1 byte data. It sends the column address. And this column address is used to multiplex out every single 1 byte inside this 2 kilobyte row buffer. So you basically have a very wide multiplexer and you select the byte you want. In this case, the 0th byte in that particular row buffer. Sounds good, right? You know how these are built. This is just a bigger memory. We actually built something like this with D flip-flops. Now we're going to talk about DRAM. Does that sound good? This is actually fascinating, I think. Okay, so this is how once the command comes, the multiplexer operates and the data gets multiplexed out and it goes on the bus to the processor chip. Okay, this sounds good. Now, if the memory controller wants to access row 0, column 1, it can do an optimization because row 0 is already in the row buffer. So we actually already read 2 kilobytes of data inside this row buffer. It's in the sense amplifiers, and the memory controller can record that and know that. It has to actually record that and know that. And now, if the processor wants to access row 0, column 1, the memory controller say, oh, the row is already in the row buffer. I don't need to activate it again, meaning I don't need to supply the row address again. I don't need to go through the row decoder, etc. It's already there. So I just want to, this is called a row buffer hit. And we're going to see caching soon. This is actually an example of a cache, which is really fitting here. So we've already accessed that 2 kilobytes of data. Now let's actually access the second column in that data, or column 1 in that data. So a memory controller realizes that it's a hit. It supplies column address 1, which multiplexes out the next bytes compared to the column address 0. And now the data comes out. Sounds good, right? This access latency is clearly faster, shorter, because we didn't have to access this huge array. We just needed to access this row buffer using a column address. We just need to go through the column multiplexer. So this is an example of caching. We're going to introduce the notion of caching. Basically, we accessed a lot of data initially, concurrently, and then we put it inside the row buffer, which is an example of a cache, which is essentially a circuit that memorizes the data or remembers the data. And then if we want to access the same row again, the access is much faster because it's already there in the cache or row buffer. Okay, let's take a look at another example. If the processor wants to access row 0, column 85, Then again, the memory controller recognizes this is a row buffer hit because row 0 is already open inside the row buffer. And then it supplies column address 85, which triggers the multiplexer to multiplex out the data from the row buffer, the appropriate byte column 85 from here. Now, if you can think of how a processor accesses data, let's assume you're going through an array and your data is all mapped in the row buffer, entire 2 kilobytes. If you're accessing every single byte, what you can do is you first access 1 byte, column 0, column 1, column 2, column 3, column 4, column 5, column 6, column 7, column 8, until column 128 or so. Basically, you can go through the entire elements that you're accessing, and they will all be almost, except for the first one, they will all be row buffer hits. So the access will be faster because you have the structure called row buffer that's a cache. Makes sense, right? Now, the problem happens if the processor wants to access row 1. The memory controller gets this address from the processor, row 1, column 0. Memory controller checks in this bank. Of course, we're looking at a single bank here. If this goes to a different bank, that's a different issue. In this bank, row 0 is open, but I want row 1. And then the memory controller says, okay, now I have to do something. First, I have to close the row 0 because there's a conflict. I cannot open row 0 and row 1 at the same time. This is only a single row that I can cache or buffer. So this is a conflict. The memory controller first writes back the row. It's called pre-charging. It's not exactly write back, but it could be write back also, depending on whether you updated the data. It writes back the row into the array. And then, so it takes time. And then it supplies row address 1, which goes to the row decoder. It activates the word line belonging to row 1. And then the bit lines from the cells that are in row 1 get connected to the sense amplifiers, corresponding sense amplifiers concurrently, the entire 2 kilobytes. And the sense amplifiers sense it, make the data strong inside the row buffer. And now the row buffer can be accessed because it contains the contents of row 1. Now the memory controller needs to send the column address 0, which belongs to row 1. And then the column mux multiplexes out 0th column. Now you've seen this conflict took a longer time, right? Row buffer hits was fast. Row buffer conflict is slow because row buffer conflict says you need to write back the current row in the row buffer and open another row and then do another access. So there are 3 steps to do this. You need to pre-charge or write back the current row. You need to activate the next row and you need to send the column address to get the appropriate column. Okay, this is actually exactly how a DRAM chip operates. We're looking at just single bank over here. Ideally, of course, you would like to maximize the row buffer hits, right? So this is affected by a lot of things, how you map the data into your banks, how you map the data into your rows, what are the access patterns that happen from the processor. So if the processor is always sequentially accessing data and the data is sequentially mapped in the row buffer, that's good. You get a lot of row buffer hits, like I explained. If the access pattern of the processor is random, you always keep accessing random addresses, what happens is you'll get row buffer conflicts, right? Because of the nature of randomness, right? You will not access, if the accesses are truly random, then the probability of hitting in the row buffer is very, very, very low. You can actually calculate that probability with true randomness. Then you will actually get row buffer conflicts and your access latency is much longer because you keep writing back the row, activating the next row and doing the column access. This is why the memory performance matters a lot because in terms of latencies in DRAM, we're talking about 25 nanoseconds for a row buffer hit, give or take, and 75 nanoseconds for a row buffer conflict. Let's say it's in that order. Doesn't sound very good, right? If you think about the processor frequency today, 5 gigahertz, 75 nanoseconds is 75 times 5 cycles. And I can do the calculation. That's more than 350 cycles, processor cycles. Earlier, we were talking about 1 cycle. Say 1 cycle here in the processor. Remember that, saving 1 cycle, right? Data forwarding, etc. So we did all of those things when we built the pipeline. Now, once you go into the memory hierarchy, if you're waiting, this is why a lot of the processors are waiting for data because the latencies here are much, much longer. Even though we try to still optimize the latencies, they're still much longer. Okay, I already said this is an abstraction, so we're going to go into a little bit more detail. So it turns out this is very hard to build. Even this huge bank is hard to build, as I said, because the interconnects are much longer. So what people do is they partition the array into smaller subarrays. These are called subarrays. When you access data, you actually activate one subarray, and then you sense the data in a local row buffer. So what you do is you bring the data only 512 rows. So the interconnects, the bit lines are actually short. And this enables you to sense the data much faster and also more reliably. And then you have bigger interconnects that are not exactly shown here. Actually, they're shown kind of here, but it's not actually a very accurate picture. I'll show you better pictures soon. Essentially, you have bigger interconnects that drive out the data out of the chip. So you bring the entire row into a smaller array, subarray over here, a smaller local row buffer. And then if you want to access a column, there are bigger interconnects over there. That's just for you to think about. And this is actually a more complicated picture that's showing the row that you're accessing thing. I'm not going to go through this, but I'm going to go through some animations. You can read, this paper actually has a very nice overview of the DRAM subsystem from the ground up. We're going to look at an example right now inside a DRAM chip, because I want to go into a little bit more detail as to how this thing works before we look at different technologies. Does that sound good? Okay, you can study this picture on your own. It's going to be very similar to what I'm going to describe with animations. So let's take a look at this again. So this is another DRAM module. It looks like this internally. And there are a lot of goals in DRAM design, actually, which I'm not going to talk about right now, but cost is one of the most important ones. Latency is usually secondary to cost. The goal usually is capacity. How do I get high capacity? High capacity means you dedicate most of your area to the array itself. You don't want a lot of area in the peripheral circuitry, okay? Latency is important, so we will divide things into hierarchical structures, and then there's bandwidth, parallelism, power, energy, reliable, security. There's a lot, basically. Okay, let's take a look at this in a little bit more detail. So here you can see actually 8 banks, one bank over here, and then it's basically replicated over here. We're going to look at different structures inside the bank. And this is cartoonish because we're going to see 2 different subarrays over here, not really in a DRAM chip. You have in a bank maybe 64, 128, maybe 6 subarrays. But I'm going to introduce the sense amplifier because this is going to be interesting to you, hopefully, because this is our cross-coupled inverter, if you remember earlier. This is what SRAM is. So in a DRAM chip, you have this SRAM type of structure. We're going to modify it a little bit to make it work with DRAM. Essentially, you have a cross-coupled inverter. This is our sense amplifier. Okay, we're going to modify it slightly. We're going to add an enable signal. When this is enabled, when it's disabled, it's not sensing. When it's enabled, it does some operation. So basically, there are 2 stable states of this, and you can also imagine this. When this is enabled, you can have VDD, meaning high voltage on top, and low voltage over here. You can say this is a logical 1, because we're going to connect the subarray over here. So essentially, this is a logical 1, and this is a logical 0. Top is 0, and the bottom is high voltage. When this is enabled. When this is disabled, it's going to be, we don't care what the value is, but we want to set it to some reference value so that we can sense things. I'm going to go through the sensing operation a little bit. So what's the sensing operation? Basically, there's some voltage on top. We're going a little bit into the analog domain a little bit, but bear with me. There's some voltage on top, and there's some voltage on the bottom. VT, VB, top, bottom. When the sense amplifier is enabled, the sense amplifier checks whether VT is greater than VB because of actually the way things operate over here. You don't need to go into a lot of detail. If VT is greater than VB, this circuit amplifies VT to high voltage and the bottom voltage to 0. So this is the basic operation of sensing that we're going to build on, and we're going to build DRAM with. That's the basic idea. This is what the sensing circuit does. You need to modify a cross-coupled inverter a little bit to make this happen. You don't need to know exactly how that works. You can learn about it on your own. But this is it's essentially a SRAM cell. So now let's connect it to a DRAM cell. Remember, a DRAM cell is a capacitor. We store charge in a capacitor. And a DRAM cell has 2 stable states. One is the empty state, meaning there's no charge in the capacitor. Let's call this logical 0. And the other is fully charged state, meaning there's full charge in the capacitor. Let's call this the logical 1. Now we're going to see how we sense these states. The issue with the DRAM cell is because we want to maximize capacity, we want to make this capacitor as small as possible. It's amazing, actually, how small these capacitors are in DRAM today. Its dimensions are much smaller than some of the other circuitry that we have. And it's very hard to make it work correctly also. Okay, but basically, these are small. They cannot directly drive circuits. So you need to sense what's inside this capacitor to understand whether it's a 0 or 1. You cannot just connect it to a circuit and say, okay, if this capacitor has charge, it'll go and drive an AND gate, for example. That's not going to work. You need to have the special sense amplifier. And when you read this actually reading destroys a state also, because when you actually sense, when you actually read the charge over there, you're actually taking the charge out. So you need to replenish the charge. Whenever you read DRAM, you need to put the charge back in if you want to keep the state that you read. Okay, so this is how we are going to sense the cell. Basically, this is our capacitor. This is our sense amplifier. We would like to sense 0 over here clearly, and we would like to sense 1 over here. So this is ideally what we would like to happen. So we're going to connect the capacitor to the sense amplifier using an access transistor. This is actually a transistor. We've seen transistors before. This access transistor will enable us to connect the capacitor to the bit line. And then this bit line is connected on this end to the top of the sense amplifier. And then there's the other end of the sense amplifier. So basically, these are what we have seen earlier. This is a word line. I'm showing you only one cell over here. But this is the access transistor that's connected to a word line, which is not exactly shown here. The control over here is the word line. We will see that later on. And then this is the bit line. So I'm showing you one cell, but you can imagine a grid of cells, two-dimensional array of cells that we're going to build soon on top of this. But let's look at this operation. If you enable the access transistor, the capacitor gets connected to the bit line. So it actually starts sharing its charge. That's called charge sharing. It shares its charge with the bit line. Okay, I forgot something very important. You basically set the different ends of this sense amplifier, the top end and the bottom end, to a voltage level of half VDD. Initially, they're both equal, and the sense amplifier is not enabled. They're not connected to each other initially. Okay, what happens is, because we want to sense whether this is lower than VDD or higher than VDD. Okay, so if this charge, when you connect it to the bit line, what happens is it shares a little bit of charge to the bit line, and this becomes VDD plus some delta value, let's say, right? Or gamma or epsilon, whatever you want to call it, right? Essentially, now the circuit, there's some charge that's shared to the bit line, and this bit line is not VDD anymore, one half VDD anymore. It's VDD, one half VDD plus something. Now, if you enable the sense amplifier, because of the operation that I described earlier, because this side, the top voltage is greater than the bottom voltage, sense amplifier will slowly, and at some point fast, amplify the top value, top voltage to VDD, and the bottom voltage to 0. This is how you sense a very small charge value and then amplify it to the high voltage level that you want to use in circuits. Okay, this is the operation of DRAM. Now you know exactly how all main memory in the world operates. This is how it operates. Okay, now let's see what we can build on top of it. And then once this happens, actually a very interesting thing happens. Once you amplify the charge over here, this becomes VDD. And the sense amplifier is now strong. This charge goes back because now the charge is huge over here. And that charge goes back and fills the capacitor. Right? That's how you replenish the capacitor. This is called charge restoration. So you connect the access transistor. Once you connect the access transistor, the cell shares its charge with the bit line. And sense amplifier senses that charge, amplifies it, and then restores the charge into the cell again, so that the cell has 1 and the sense amplifier sense 1. And this is the stable state after that point, after restoration. Of course, these operations take time. So they're nanoseconds. It takes nanoseconds to make this work, because this is really small. If the DRAM cell was much larger, it would take faster, actually, because a lot of charge will get out and things will operate faster. But a DRAM cell that's large is not good for capacity, right? Today, we want capacities that are huge for many, many reasons, machine learning being one of them, but many applications. If you want capacities to be huge, the cell needs to be much smaller. Okay, now let's build it higher. So this is our capacitor, access transistor, and sense amplifier. This is our building block. So we're going to build a subarray. This is our bit line now. On this part of the bit line, you have these 3 cells. You can also connect something else on the other side of the bit line. It operates exactly the same. It's just the opposite side, right? This is our bit line now. It's a single bit line. It could be 512 cells connected to it. And then this is our word line now. This is our array structure. You just need to add the same thing and replicate it, right? Now you see a 2-dimensional array structure that's part of our subarray. Okay? And then you have to have a sense amplifier enable signal, of course. And then you connect your row decoder. This is 4 by 6 array, as you can see, but in real life, it's 512 by 512 potentially. This is an array of sense amplifiers. In real life, it could be 8 kilobits, 2 kilobytes. And then these are the cell arrays that belong to the same subarray. Now you put more subarrays together, more row decoders, and that gives you a DRAM bank. And then you need to actually have a way of connecting what you sensed to the I/O outputs of the bank, meaning because you want to output it out of the chip. So you need to have additional interconnects that connect the sense amplifiers to the bank I/O. But these don't need to be very wide. It can be only 64 bits, for example, in the bank, 8 bytes, for example. It could be even 1 byte. Okay, and then the address needs to get distributed. So which row you're accessing depends on which subarray address you have. So this is a physical address determines which subarray you're accessing, which row you're accessing, etc. And then there's part of the address that also gets used for column select, because if you have the data inside the sense amplifiers, then you need to select which column you're accessing, right? Which byte you're accessing. Okay, so basically that's it. I will go through this also relatively quickly, but a chip may output only 8 bits, as we have seen earlier. But this is how the 8 bits come. There's an internal bus. There's an internal bus, which is 8 bits, let's say. And each bank is connected to it. And each bank at some point can provide 8 bits, which is a single column to this internal bus. Okay? Now let's look at the steps again. So this is 2 subarrays. Assume that you have an address. You first supply the row address. And then you decide which subarray it goes to, of course, because part of the address determines which subarray it is. Assume that it's this row, and you want to access this black column in this yellowish row. You first need to activate the row by supplying the row address, which brings the data into these sense amplifiers that are local inside the subarray. You wait until the sense amplifier sends the data and amplify that, restore the cells, etc. And then the memory controller sends a read signal, let's say. I'm going to read column X here. So the memory controller needs to send this column address as well as the read command, which brings the data into the bank I/O through some interconnects that are not really shown here, which is what we saw earlier in the bank level picture, but we're looking a little bit deeper here. And then now the row is open. The row that's activated is open in the local row buffer. If you want to access some other row, you need to set the sense amplifiers to a stable state or reference voltage. Because sense amplifiers, when you open the row, the values on the sense amplifiers are essentially determined by the values that you read from the capacitors, right? Now, if you want to open another row, you need to set those sense amplifiers to a reference voltage so that they can sense another row. What was the reference voltage? The top of the sense amplifier is 1/2 VDD. The bottom is also 1/2 VDD. Now, basically, there needs to be some circuit that I didn't explain to do that, but this is the pre-charge circuitry. Essentially, pre-charge circuitry goes and changes the voltages such that first it writes back the data into the cells, which which actually happens kind of automatically, but then sets the voltages of the sense amplifier to 1/2 VDD on either side so that you can start the next access reliably. That's the pre-charge operation. Basically, row becomes closed after that so that you can activate another row so that you can sense that row reliably. Now, actually, I've demystified all of the magic. Basically, there's no magic on how this operates, assuming what I said is true. And what I said is true, essentially, all memory operates this way. All main memory operates this way today. Okay, so if you're interested, you can, if you want to do some more reading, there's a comprehensive DRAM background in this paper that we wrote. You just need to look at section 2 that builds up the DRAM. But you can also study what I just said. Any questions? Now you know how DRAM operates, which is good, because you're going to see a lot of DRAM in your life. Maybe. Okay, now let's go into how data gets mapped and how we actually access a cache line. We're going to look at cache lines later on. I've given you the, let's say, organizational perspective so far. Now let's look at the operational perspective. So I have some physical memory space, and I have some data that I want to access. Let's call it a 64-byte cache block. It could be smaller also, but usually, as you will see later in the lectures, you operate using 64 bytes. Whenever a processor wants to access some data, it wants to access 64 bytes for the reasons we're going to talk about later. I assume that this is the case, but the operational principles are the same if you want to access smaller data also. So it turns out the 64-byte cache block gets mapped to a single rank. So a single rank in a single channel. That's called a stem0 or rank 0, right? So this 64-byte gets mapped over here. And we want to access 64 bytes. So how do we do that? Let's take a look at that rank. This rank 0 looks like this. And if you remember the picture that I showed you earlier, each chip there are 8 chips in a rank, and each chip supplies 8 bits. And we've seen the internals of a chip also now, so there's no magic. Each chip supplies 8 bits, but we want to get 64 bytes, meaning if we access all chips concurrently, we'll get 64 bits. So we're going to do that. We're going to access all chips concurrently to get the first byte. And then we're going to access all chips concurrently again to get the next byte. And then we're going to access all the chips concurrently again to get the next byte, and then the next byte, and the next byte. So we're going to do 8 accesses concurrently to all of these chips to get 64 bytes. If you wanted 1 byte, you access all chips concurrently once. If you wanted 64 bytes, you access all chips concurrently 8 times. If you wanted 256 bytes, you access all chips 16 times, right? Yes, I think, no, 32 times, not 16. Okay, I can still do math. Okay, so basically for this to work, the data needs to be mapped correctly. In this case, for example, the first byte comes from, first 8 bits comes from here. The second 8 bits comes from here. The second 8 bits comes from here. So basically, with every single access, you get 8 bytes, right? So this is 1 byte, so there are 8 bytes. So you get 8 bytes over here. That's 64 bits. And then you move to the next, let's say, column, row 0, column 1 in each chip. So initially you access row 0, column 0 in each chip, get 8 bytes. Then you access row 0, column 1 to get the next 8 bytes. Then you access row 0, column 2, etc. Right? I already said this. So basically, if you want to access 64 bytes, it takes 8 cycles, 8 I/O cycles to transfer. And during the process, 8 columns are read sequentially. And the good news is it comes from the row buffer, right? Initially, it may not be in the row buffer. Initially, you get a row. It takes some time. But after that, all of these are in the row buffer, and you access row buffer sequentially. Okay, so you get row hits. Okay, so now you know actually how to access a cache block also. We're going to see how to design caches later, but the operational principle of accessing 1 byte is the same. You basically just access all of the chips concurrently so that you get essentially 8 bytes, and then you pick the byte you want over here, right? You can decide which byte to pick, okay? Okay, this is one, I should also say that this is one way of designing DRAM. This is the common way in general purpose computing. There could be other ways to design, but if you look at DRAM today, HBM, high bandwidth memory, for example, LPDDR, low power DRAM, there are different kinds of DRAM, but all of them operate based on the same fundamental principles. At the core, the array is essentially the same. What matters sometimes is the interface. For example, how do you design the interconnects so that they're high speed or they're low power, etc. But these are below the abstraction level of this course. There are also architectural issues, but again, we cannot cover everything in this course. Okay, now I'll move to memory technology. Although we have been talking about memory technology, let's talk about DRAM a little bit more. Now you know DRAM a lot. I'll go through this relatively quickly. I've already said everything over here. It's dynamic. Capacitor charge states indicates stored value. Whether the capacitor is charged or discharged indicates storage of 1 or 0. So you have one capacitor. That's why this is very dense. That's why many memories are built this way. And you need an access transistor to access that capacitor so that you can connect the capacitor to the bit line and then sense it. And the row enable or word line enables that access transistor. And you know exactly how this operates now. Now, there's another issue with DRAM, which is when you have capacitor and when you have this sort of access transistor, it turns out there's some path that is still active. So there's some leakage that happens through this capacitor. There's an RC path. Even though you have not enabled the row, meaning enabled the access transistor, there's some leakage that happens. So DRAM cell loses charge over time. You stored some charge, but it keeps leaking over time. This is one of the reasons why it's dynamic. So it needs to be refreshed. So this sort of memory needs to be refreshed periodically. And today we're refreshing. So for example, in my pocket, my cell phone is refreshing every single cell every 32 milliseconds or so. At high temperatures, this could be even worse. While operating, this laptop is refreshing all of its memory at this point, once in a while. Every 64 milliseconds or every 32 milliseconds, memory controller goes and refreshes every cell in DRAM. Every row, I should say, because it happens at the row granularity. So refresh is really reading the row and writing it back so that you restore the charge completely, so that you don't get data corruption. Okay, a memory that doesn't have this problem is SRAM. SRAM is static random access memory, and you've seen this before also. Now we have 2 cross-coupled inverters that store a single bit. This feedback path enables the stored value to stay in the cell as long as it's powered on. Both of these are volatile memory technologies. For these to keep the data, they need to be powered on. They lose their power. Once you lose the power you will lose all the data in DRAM and SRAM. In this case, you have 4 transistors for storage because you know from lecture 1 or 2 that each inverter is 2 transistors in CMOS technology. And then you will have 2 transistors for access. And I explained the operation of this briefly last time. I will not go into the details again, but you can see immediately that this is quite expensive, right? You have 6 transistors already, and there are versions of this that are 8 transistors, and they're bitline and bitline bus, so there's some differential sensing. But in the end, whether you're designing SRAM or DRAM or some other technology, a lot of memories, actually almost all of them, look like this. So you basically have a bank. Internally, the bank actually can be subarrays, etc., like we have seen. But let's look at the bank abstraction right now. You have a 2-dimensional storage array, and then you have a row decoder to access the row. And the read access sequence happens to be you decode the row address, drive the word line. In this case, it should be word line. You drive a single word line. Assume that we want to access this row, blue row, and we want to access the red column. And then the selected bits, the selected bits drive the bit lines. You read the entire row. You amplify the row data. In some different technologies have different ways of amplifying. You've seen DRAM quite a bit. And then you decode the column, the least significant bits that are coming from the address. Most significant bits are used for the row. Least significant bits are used for the column. Least significant bits enable this multiplexer to multiplex the byte or bits or whatever granularity you're accessing out from the memory. And then you pre-charge the bit lines for the next access. So DRAM or SRAM, they both operate this way. You've seen how DRAM operates exactly. We're not going to go into SRAM in detail. SRAM is a little bit easier, actually, except when you go into extremely small technology nodes. When you go into small technology nodes, all of the charge levels are also small, so you get noise issues, etc. But we're not going to go into those issues right now. But still, the operational principles are the same. That's the beauty of memory. Like, they all look like this in the end. Okay, so let's take a look at SRAM a little bit more. This is our SRAM. SRAM is used to design all of the on-chip memories today. So if you look at the chip, the processor chip over here, most of it is SRAM. The reason most of it is SRAM is most of it is caches, as we will talk about. So all caches are designed using the SRAM technology. So this is our bit cell array in SRAM. Let's call it a bank again. And you can see some numbers over here. You use n bits of the address to decode one of the rows. Enable the word line. And essentially, the access is the same, right? So you read the entire row, and you do differential sensing. So the sensing circuitry in SRAM is a little bit different, and then you select the column that you want, and then you get the data out. And if you want to access another row, you pre-charge all the bit lines. Okay, essentially, I will not go into this detail, but access latency is dominated by how fast you can drive the row, word line, and how fast you can drive the bit line. So these are interconnects, if we're thinking about it, right? That's why increasing the size of this in terms of both X and Y axes increases your latency, right? Cycling time is basically how fast you can access the next row. It's really dominated by the interconnect latency as well as how fast you can pre-charge all the bit lines, meaning prepare the array for the next access. So these are all important latencies. But SRAM doesn't have the refresh problem. So because of the cross-coupled inverter, SRAM kind of amplifies. Once you store some data inside the SRAM cell, it keeps amplifying the data. It doesn't have the charge leakage problem because of the cross-coupled inverter. Whereas DRAM, it doesn't have a feedback mechanism to amplify its charge. As a result, it keeps losing and losing and losing charge, so you need to refresh it once in a while. Right? Okay, but SRAM is more expensive, as you can see. So DRAM looks like this. I'm not going to go through this in detail, essentially, because we've already gone through this a lot. But essentially, we've discussed it. So 2 differences from SRAM. You have destructive reads. Whenever you access a row, you destroy the data inside the capacitor, so you need to amplify them, restore the charge. And we've seen exactly how that works. And your charge gets lost over time, so you need to refresh it. Okay, we've already discussed all of these, so this is for your reference. But they look essentially the same if you think about it, right? It's just the technology. It's just the bit cell, the storage technology that's different. Capacitor versus cross-coupled inverter. Plus, access circuitry needs to be a little bit different also to take into account the storage medium. Okay, let's compare these 2 because this is actually important. This is why we are going to memory technology. We looked at memory organization. Now, memory technology, we're looking at DRAM versus SRAM, and these technologies actually have different trade-offs in the end. That's why we'll build a memory hierarchy soon. So DRAM is, in general, slower access because capacitor sensing is a much slower process. You're really reading from the capacitor that's really small, and you need to amplify that. As I said, this takes nanoseconds, many, many nanoseconds. But because capacitor is so small, and also it requires only one access transistor, it's called a 1T, 1C, one transistor, one capacitor cell. It's very high density. So you can actually have very high capacity in a given area. As a result of that, it's also lower cost per bit. And when you talk about memory, you usually talk about cost per bit. So cost per bit is very low. As a result, all memories today, big memories, are DRAM. If you want storage, it's going to be flash memory, which I'm not going to talk about, but I will mention that later on. The downsides, the green ones are good, the red ones are bad, basically. It requires refresh. Basically, refresh is not good because it consumes power, it leads to performance issues, and also it has extra circuitry. Now, manufacturing is also different. So SRAM is actually logic. If you look at everything that I said over here, there is no capacitor. There is no extra difficult sensing circuitry, etc. So SRAM manufacturing is compatible with logic process. So you can actually build it directly inside a processor chip with the logic CMOS processor chip with the logic structures that we have seen earlier. Now, DRAM introduced a capacitor that we have never seen, let's say, in earlier lectures, except for last week. That requires actually a very different fabrication technology. And as a result, this cannot be put together with the CMOS logic easily, I should say. It's very inefficient to put it together. So this requires a completely different fabrication fab, if you will. You need to build billions of dollars of fab that's completely different for memory. That's why memory companies are very different from logic companies today. That's how the industry evolved, unfortunately, or fortunately. It's a bit unfortunate because if you marry these together, you can actually get a much better computing system. We're going to talk about that. Okay, so SRAM is exactly the opposite of DRAM. It's faster access because there's no capacitor. Unfortunately, it's very low density, 6T cell. It's much smaller. Given a single bit requires much bigger area to store. As a result, it's much higher cost. As a result, we don't build large memories with SRAM. Right? There's no need for refresh. That's good news for energy, performance, and circuitry. And you can put this together with CMOS. As a result, you can actually, all on-chip memories are SRAM. Let me give you an aside. These are not the only two technologies. This is an area that I have worked on quite a bit. I actually work a lot on memory in general, but there are other technologies. I'll give you one example over here. Phase change material. So there's some phase change material. One example is chalcogenide glass. It exists in two different states, amorphous and crystalline. You can represent it something like this. So it looks like this, basically. This is the glass over here. In one state, this has low optical reflexivity and high electrical resistivity. In the other state, opposite state, it has high optical reflexivity and low electrical resistivity. Meaning, you can read this optically, depending on the state. You can shine light on it, and if the light reflects back, you can figure out whether you have stored a 1 or 0. Now you can see that this is a very complete different technology, right? It also requires a complete different fabrication process, but this is a memory that can store data also, right? And or you can actually build something that detects the resistance. So you can do this reading in two different ways, optically or electrically, which is fascinating. And people have actually worked a lot on figuring out how to do this reading fast electrically, because optical reading is usually slow. Unfortunately, people have worked on that technology. If you had a CD, rewritable CD, how many people know about rewritable CDs? Okay, it still exists. Okay, I think it's getting an older technology, let's say. If you have a rewritable CD, it works based on these optical principles, slow. But if this can be made main memory, you can use it, you can design circuitry to detect resistance. I'm not going to talk about that in detail, but you can read papers again. So we worked on actually enabling this as main memory. So this could be very dense. This kind of technology can be extremely dense, as you can see from CDs. DRAM, for example, it has some downsides, as we will see in the next slides. PCM has some upsides. So if you can enable this technology, you can have a much better main memory. And this is a paper we wrote. And later, Intel actually designed the 3D point. Unfortunately, they discontinued it currently. It's a bit sad because Intel has a lot of problems these days, in addition to technology problems. But basically, it's a memory module that Intel designed, let's say, 10 years after we evaluated and envisioned it, etc. And you can see that it's actually huge, 128 gigabytes. And its costs can be much lower. So if another technology comes in, and if it can be manufactured reliably it could actually be very good for having much bigger memories. Now, let me give you the differences between DRAM and PCM. So DRAM is actually faster access in this case compared to PCM, it turns out, because it has a capacitor. Capacitor is faster, whereas PCM turns out to be slower access because you need to have heating and cooling to change the phase of the memory. DRAM is lower density, which is interesting because capacitor is less scalable, it has higher cost, whereas phase change material is much more scalable. You can make it much smaller than the capacitor itself. DRAM requires refresh, phase change memory doesn't require refresh. DRAM manufacturing, there needs to be fabs. Unfortunately, PCM manufacturing, there needs to be also fabs. It's not mature today, and that's one of the reasons why Intel discontinued it. They were not able to, at least under the financial constraints they were not able to make the fabrication process, let's say, extremely good. DRAM is volatile, meaning loses data at loss of power. PCM is non-volatile. It doesn't lose data at loss of power, meaning it's a storage technology, but it could also be a main memory technology at the same time. DRAM has no endurance problems, as far as we know, but PCM has endurance problem. This is one downside. I will introduce it very quickly, and then we'll take a break soon. But basically, if you keep writing to a cell, after some point, the cell wears out in phase change memory. This happens in flash memory technology also, meaning you cannot read or write from the cell anymore. This is a very technology-dependent problem, but flash memory, SSDs, solid-state drives have the same problem. But DRAM doesn't have that problem, that's good. Unfortunately, PCM has higher access energy than DRAM. So you can see that now we have trade-offs, right? Reds and greens. Whenever you have reds and greens, it's good to think about how am I going to place this sort of technology in the memory hierarchy? And we're going to talk about that in the second part of the lecture. I'm going to pick it up from here, talk a little bit about technology, and then we're going to build up to memory hierarchy and caches soon. So let's take a break until the bell rings, and we're going to talk about all of these. Okay, everything is good? Okay, now we can continue. So now you all know how DRAM operates in a lot of detail, SRAM operates in some detail, and now at least a high-level overview of PCM. You can see that there are different technologies. I will also distinguish between charge versus resistive memories, especially on the main memory side. Very quickly again, the difference between DRAM and phase change memory is DRAM actually is charge-based memory. Flash memory is also like that. SSDs are also like that, but we're not going to talk about that. You basically write data by capturing some charge, and you read data by detecting some voltage. You don't need to go through this in detail. Whereas resistive memories, phase change memory, magnetic memories, for example, memristors, which you may have heard of, which we're not going to go into, you essentially read data by detecting some resistance. So these are two fundamentally different types of memories. The first one is volatile in general, although it could be non-volatile also, depending on how you do things, whereas the second one is non-volatile. Okay, let's go through this a little bit in detail. So basically, I've already given you a phase change memory. You basically store charge in terms of the phase of the material because resistance is determined by phase. There are some other interesting technologies like spin torque transfer, MRAM, magnetic memory. You have a magnet, and the polarity of the magnet determines whether you store a 1 or 0. You have a reference magnet, and then you have a magnet that's free magnet. And whether the magnet at the top is parallel or anti-parallel in terms of polarity to the reference magnet determines whether you have stored a 1 or 0. And your resistance is really determined by the polarity. And the way you read or write those memories is by injecting enough current so that you change the polarity of the magnet to a different direction, which is very fascinating. This could also be potentially a very large-scale memory. But these are all relatively emerging technologies. They're not there yet, so you cannot buy these easily in the market, except for some niche applications, for example. And then there's the memristors. You basically inject some current to change the atomic structure of some material, and the resistance is determined by the distance of the atom. So you need to have reading circuitry to determine that resistance. So you can see that these are all different memories. They have all different reading mechanisms and writing mechanisms, but in the end, their structure is the same. The organization is two-dimensional arrays in the end. It could be three-dimensional in some cases, but we won't talk about three-dimensional here, where people are just building to three dimensions now. Okay, so if you're interested in this, there's a lot more in some other lectures, which we don't really have time for, so I'm going to flash these slides. Flash memory, actually, the reason I talk about these is very important. So these emerging memory technologies, you may say, okay, why is he talking about this? These don't even maybe exist. I cannot even buy them in the market. Well, there was a memory technology that you couldn't buy in the market. It didn't exist in the 1980s, 90s, almost a lot of 2000s. And that's flash memory, SSDs today. So that flash memory operates based on, again, some charge-based principles. It can be made non-volatile. Essentially, this was a very doubtful emerging technology for many, many decades, like 30, 40 decades almost. And then people have figured out how to manufacture it nicely. And also people have figured out how to use it nicely at the application level. For example, people have figured out how to store images on it, how to store music in it, how to store media in it. And as a result, that flash memory technology is really what enabled a lot of the innovation at the mobile system. So this thing is very usable today because it has a huge storage associated with it. And that huge storage is really flash memory. If flash memory wasn't there, you would be carrying a huge cell phone with a lot of DRAM or a magnetic disk, which is not very good, right, clearly. So these emerging memory technologies can enable new applications and new use cases. And that's one of the actually important questions that people are asking in research. What can we do with them to make the systems a lot more efficient? Okay, I'll leave it at that. But if you look at the flash memory, actually, it's very complicated and it's very interesting. But if you're really interested in this stuff, you can read papers. We're not going to go into that or take our advanced lectures. Okay, there are lectures, as you can see. There is an SSD course for the same reason also. Okay, so I'm going to talk maybe in the last lecture about processing in memory. So one of the things that we do today is, I will kind of flash this thing over here. One of the things that we do today is you have processor, you have memory. What I've described so far is processor and memory are, processor is always asking memory for some data to come, to get, right? Or it's writing data to memory. Why not put the processor on the memory side also? Based on what we discussed in the last lecture, putting the processor on the memory side is a very interesting proposition. And this is something that's going on in research that we're trying to enable. Again, this is like looking into the future. because I'm finishing the memory technology lecture. We're going to talk about memory hierarchy soon. And we have a processing in memory course also if you're really interested. Now we're going to go into memory hierarchy. That was kind of a researchy ending to the memory technology, memory organization lecture. Now we're going to build memory hierarchies. And if you look at memory today, it's all about hierarchy in the end. Most of a system today is memory. You have SRAM caches, another level of SRAM caches, another level of SRAM caches, another level of SRAM caches, and then DRAM, a lot of DRAM, and then a lot of storage. So most of the system is memory, as we discussed in an earlier lecture. So again, I'll flash through these pictures that I showed you earlier. A lot of it is memory hierarchy, right? This is an example of memory hierarchy, for example, right? Most of it is really memory. Older system, actually, as I said last time, you had some caches, but they were outside. But with Moore's law and very large-scale integration technologies becoming very good, all of these memories became part of the processor chip. So the reason processor chip is dominated by memory today is because it's kind of ate all of the other chips around it. And you have now a single chip with billions of transistors. Actually, we're getting closer to trillions of transistors. That's depending on how big of a chip you want. With a lot of it is memory. Okay, you can see that this is how it got integrated. So the level 2 cache got integrated. So we're going to go into the caching, basically. We're going to look at how these caches operate. And again, if you look at a system today, most of it is caches, right? You've seen a lot of these pictures before. Okay, so why are we going to talk about it? Ideally, you would like an ideal memory. And you've seen this picture before. We want 0 access time. We want infinite capacity, 0 cost, infinite bandwidth, 0 energy. Clearly, we're not going to get all of them. We're not going to get even one of them, right? Because 0 is a very low number and infinite is a very high number, right? Okay, the problem is, but you would like to approximate it, right? Whenever you want to build a system that's good, it's good to think about the ideal. So idealism is good. Of course, you need to marry idealism with reality, and you need to understand how you can try to achieve or approximate that ideal with real, right? So the problem is that ideal memory's requirements oppose each other completely. Bigger is slower, and you know that from today's lecture and from last times. Faster is more expensive. Higher bandwidth is more expensive. If you want to actually access many things concurrently, we've also seen that today. You want to enable a lot of pins. So bigger takes longer to determine the location. Faster, there are multiple faster. Basically, you can make the array smaller, but then the peripheral circuit becomes bigger, etc. But memory technology also. SRAM is more expensive than DRAM. DRAM is more expensive than SSD. SSD is more expensive than disk. Disk is more expensive than tape. Right. This is the hierarchy, actually. And higher bandwidth is more expensive because if you want higher bandwidth, you need more banks, more ports, more channels, higher frequency or faster technology in the end. Okay, so let's give you some numbers. I don't expect you to read all of these, but these are some numbers circa 2023 or so. These are some technologies that are in use at the time. But you can see that bigger is slower. SRAM can be small. There could be bigger SRAM also. You go from smaller nanoseconds, like sub-nanoseconds, in DRAM about 50 nanoseconds on average, let's say. But you know that DRAM is also not the same, depending on what row you're accessing, whether it's in the row buffer or not. So this is actually the Optane DIMM, which is the phase change memory DIMM. You can see that it's about 300 nanoseconds. It's longer than DRAM with one technology. And then you go to SSDs, it becomes gigabytes and terabytes, and the access latencies becomes microseconds. It's very long, so you don't want to access SSDs in general, but that enable access to our storage, right? So you still want to have SSDs. This is PCM, phase change memory-based SSDs. And then if you go to flash memory, it's actually more microseconds. And then hard disk can be on the order of milliseconds, right? And then faster is also more expensive. This is the dollars per megabyte comparison. You can see that SRAM is multiple orders of magnitude, like 50x, actually less than 50x. Yeah, about 50x. No, that's 500x, right? 500x more expensive than DRAM per megabyte. Phase change memory is cheaper than DRAM slightly. Flash memory is much, much cheaper than DRAM, as you can see. And hard disk is even cheaper than flash memory. So this is good to think about. I mean, you can also figure these out on your own, but this is one example. And these scale over with time. I'm going to show you a 2011 version of this, which is much more expensive and slow, not as slower, but much more expensive. So other memory technologies may have their place as well, right? Okay, so this is a table view. I should have probably gone through this because this is a much better perspective, as you can see. Bigger is slower. As you go from memory device, latencies increase significantly, and faster is more expensive in terms of dollars and chip area. So this is the energy view. I'm not going to go through this, but energy per access also increases as you go from smaller memories to bigger memories. So for example, if you want to access a hard disk, it's on the order of 60 millijoules, for example. Whereas if you want to access SRAM on chip, it's picojoules. This is the reason why we don't want to move data between different types of memories, right? Because you go through a big interconnects and you waste a lot of energy. You've seen in the last lecture how much energy is wasted on accessing memory, right? If you had some processing on the memory side, we wouldn't be wasting a lot of energy. Okay, this is the 2011 version if you're interested in comparing this one to the 2023 version. Okay, so why do we want memory hierarchy? Basically, we've seen these technologies and we've seen that ideal memory requirements oppose each other. Basically, we want both fast and large in the end. The problem is we cannot achieve both with a single level or single type of memory in the end. So the idea of a memory hierarchy is have multiple levels of memory or storage, that's called a storage medium, and they get progressively bigger and slower as the levels become farther and farther away from the processor. And have a mechanism to, as much as possible, ensure most of the data that the processor needs is kept in the faster levels. So you want to access some data, hopefully it's in the faster level and not in the far away level. Right? So you get high capacity by having many levels, let's say multiple levels, but you can access the faster level fast, and you try to ensure as much as possible that you're accessing the faster level to get the data and you don't need to access the rest. That's the idea basically. So a memory system at a very high level looks like this. You have, this is actually just cache as a main memory, but you can extend with SSDs, etc. You have some caches that are small and fast, and you have main memory that are large and slow. You want to access the data from caches. And then just like what we did with memory, there's hierarchy. Inside the caches, you can have smaller and faster caches, and then a little bit larger and slower caches, and you can have a hierarchy over there. And ideally, you would like to access the smaller and faster caches, smallest and fastest cache, right? You can also build main memory with smaller components that look like that as well. Okay, so basically, it looks like this. You have some fast and small components, memory, and then you have large but slow components. Okay, let me go back. With good locality of reference, memory appears as fast as this small component, but also as large as this large component. That's the idea. We want to get the best of both worlds. We're going to talk about locality of reference. You need to have a nice access pattern, as we will see. So you move what you use here, and you hope that you're going to access what you use again and again and again, right? So row buffer was one example, right? You moved a lot of data into the row buffer in DRAM, and you hope that you access the row buffer again and again and again and again so that you don't need to activate another row in DRAM. So that was an example of a fast and small cache from the DRAM perspective. We're going to build SRAM caches that are faster and smaller. Okay, and then you back up the large data here. Hopefully the data that's not going to be used stays here, but when you need it, hopefully it gets back and then you keep accessing it, right? That's the locality of reference, basically. The data that you access heavily gets into the fast and small components, small memory components, cache, and you keep accessing it frequently, and hopefully you don't access this large but slow components often. Okay, and then you can actually generalize the idea. You can have a next level and a next level and next level, right? As you go from large components to small components, you get faster per byte, and as you go from small components to large components, you get cheaper per byte. So clearly there's a benefit to speed as well as capacity, because there is no one size fits all, because it's a very fundamental trade-off, latency capacity trade-off. Okay, so that's basically the trade-off, right? Fundamental trade-off is fast memory is small and large memory becomes slow, right? And this is the idea of the memory hierarchy. This is an example over here. You have CPU, you have registers. Actually, when we introduced registers, when we talked about the von Neumann model, we talked about temporary storage, right? That is part of the memory hierarchy as well. It is really, you move the data that you really need, or you allocate the data that you need in the instructions inside this register file. And these are things that you don't want to access going to memory, right? That's why we introduced the concept of registers in the instruction set architecture, because you're operating on some temporary values that instructions are using and communicating with each other, right? That's the register file. That's managed by the compiler or the programmer separately from the rest of the memory. And then you have some cache, and then you have some other caches, and then you have main memory, and then you have hard disk. So clearly there are trade-offs in terms of latency, cost, size, and bandwidth as you go from left to right, latencies increase, cost of memory decreases, size of memory increases, and the bandwidth of memory also decreases. Here, your register file can be very high bandwidth because you're operating at the frequency of a CPU, a pipeline. Okay, this is another example from the book chapter that I kind of recommend you to read. This is a hierarchy with three cache levels and the main memory at the bottom level. And you can see, again, the capacity and the latency trade-offs over here. Okay, so hopefully this is clear. So why does this work? Basically, why do people build memory hierarchies? Because it's based on the locality principle. It's really a very fundamental principle in terms of both, let's say, how programs operate, as well as how humans also operate. So I'm going to give you examples. Essentially, locality means at a, let's say, loose level, one's recent past is a good predictor of their near future. So temporal locality, for example, if you just did something, it's very likely that you will do the same thing again soon. If you're paying attention in lecture, listening to me, it's very likely that you're going to pay attention. If you're not paying attention, it's very likely that you're not going to pay attention. And this is actually true. I like the sleep example. If I keep sleeping long, I'm going to sleep long. If I keep sleeping short, I actually start sleeping shorter. This is actually very interesting also observation. If you're sitting here right now, in the next nanosecond, you're going to sit here again. Right? There's this temporal locality, as you can see, probably in the next 30 seconds or until the bell rings, etc. So basically, this is temporal locality, right? Based on your actions, you also exhibit temporal locality. I also exhibit temporal locality, obviously, right now. There's another example. Since you're here today, there's a good chance you will be here again and again regularly, and that's also true, actually. People who come here regularly, again and again. People who don't come here regularly, again and again, right? That's temporal locality for you. Spatial locality is if you did something, it's very likely that you're going to do something similar or related from a space perspective. Now, let me give you an example. Every time I find some of you in this room, you're probably sitting close to the same people and or in close by seats. And that actually holds in general also. There's a spatial relationship. You have your friends and you sit together, right? And sometimes you happen to sit together in the same seats all the time or most of the time, right? So there's some spatial locality also, right? In space, you're correlated with each other also. Okay, that's one example, clearly. I'll give you some more examples. But basically, similar to this, memory has locality as well. In a typical program essentially has a lot of locality in memory references. I'm going to give you examples of this. Typical programs are usually composed of loops, as we discussed, right? Temporal locality means that the program tends to reference the same memory location many times and all within the same window of time. You have some variable that you need to add to some other variables. So you keep accessing that variable many times because you need to add it to many other variables, right? Hopefully that makes sense, right? So that particular variable is accessed a lot, right? You have a piece of the graph and you're doing some analysis on the graph and you're going through that graph many, many times to do this analysis, right? So that's another example of temporal locality where you're actually operating on a collection of data elements. And if you keep them in your cache, you're going to access them fast, right? Spatial means a program tends to reference nearby memory locations in space, address space in this case, within a window of time. And again, there's a good reason for this. Array references, for example, in vector processing. If your array is allocated consecutively, and if you're going through your array sequentially, you're basically accessing element 1, element 0, element 1, element 2, element 3, element 4, element 5, element 6. And if they're spatially, let's say, adjacent to each other, consecutive in memory with each other, they basically have a lot of spatial locality in that reference that you in those references that you make to the array, right? Essentially, arrays and vectors, if you remember. You often have a stride or stream of 1, for example. Even a stride or stream of 2 is okay because spatially you're close enough. Whereas if your stride was, let's say, 10 million, then you're spatially far away, right? But we don't want 10 million strides because that's not good for locality in general, right? And many programs don't have huge strides. If you remember the vector array processing GPU lectures, you basically have a lot of spatial locality. If you add 2 vectors together, for example, or multiply 2 matrices, again, there's a lot of spatial locality. Another example is instruction memory references. Because we have sequential programs in the von Neumann model, you basically go through a PC, PC plus 4, next PC, and the next PC, next PC. You keep incrementing the PC, right? And the program counter is location in the address space. You're basically going through consecutive locations in the address space. So in terms of space, you're traversing the address space, right? So these are two very good reasons why there's a lot of good spatial locality in programs. So combined with these, caches exploit both temporal and spatial locality in the end. So the basic idea, let's talk about exploiting temporal locality first, because it's a bit easier. You store recently accessed data in automatically managed fast memory. Automatically meaning programmer doesn't deal with it, compiler doesn't deal with it, hardware manages it. This is called a cache. That's a hardware cache. There could be actually software caches also, which we're not going to talk about a lot, but the caching concept is actually pretty general. This is the idea basically. If the CPU, if the processor requested a data element and with an instruction, load instruction, it puts it in a fast memory, anticipating that you're going to access it again. That's the anticipation basically. Same memory location will be accessed again soon. So basically, temporal locality principle says recently accessed data will be accessed again in the near future. And this is very strong in general. If you're, of course, accessing, if you're not reusing any data, then you're not going to get this temporal locality. But that's not true in general. So one of the earliest papers in caching was written by Maurice Wilks. If you remember Maurice Wilks, he also introduced the micro-coded microarchitectures a long time ago, multi-cycle microarchitectures. And in this paper, I'm going to read this because this is fun, because we're going to look at core memory later on as well. The users discussed of a fast core memory of, say, 32,000 words, which is very small today, as a slave to a slower core memory of, say, 1 million words, in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. It's beautiful, basically. You have two types of memories. One is small, fast. The other is slow, large. And then hopefully, you're going to access the fast one most often. Okay, so that was temporal locality. If there are no questions, we're going to move to spatial locality. So spatial locality, you basically do the same thing in space. You don't look at a single variable, but you look at a collection of addresses. Essentially, the data in that collection of addresses that are adjacent to each other, store those in automatically managed fast memory. So if you're accessing, let's say, one data using a load instruction, you look at the other addresses around it, and you bring all of that data into the cache with the anticipation that because you're accessing address X, you're going to access the surrounding addresses as well. That makes sense, hopefully, right? The processor, it accesses address X, but when it brings data, it doesn't just bring the, let's say, word that is operating on that address X, but let's say 16 words around it and brings it to the cache. And the hope is that you're going to access a lot of those words also. That's the idea, basically. Simple. To be able to do this, there are multiple ways of doing this, but one way of doing this, which is really the common way that's implemented in all microprocessors today, is you logically divide memory into equal size blocks. It's going to call the cache block. And you fetch to cache the accessed block in its entirety. This block can be 64 bytes. Remember the 64 byte in DRAM? That's why I showed 64 bytes. It's a 64 byte cache block. The processor load instruction may need only 1 byte. Doesn't matter. Load instruction goes to memory. The memory controller brings the block that contains the single byte that you really need, but it also gives you 63 other bytes around it. And that goes into the cache. And if the processor happens to access another load that references one of those 63 bytes, bingo. Meaning you already fetched that in the cache, right? It already came from memory, so you don't need to access memory at that point. That's the idea, basically. It's a beautiful idea, as you can see, simple idea. And the anticipation is that nearby memory locations will be accessed soon when you're accessing memory location X. Okay, so this is spatial locality principle, and we already discussed why this makes sense: sequential instruction access, array traversals, matrix traversals, etc. This is what was implemented early on in 1960s in IBM. This is one of the seminal papers also. For example, IBM 368085 had 64 kilobyte cache, which is relatively small for today, with 64 byte blocks. Today we have actually 64 byte blocks also, which is interesting. Okay. I like this bookshelf analogy for caching also. So you may have books in your hand that you're using when you're studying. You're going to reuse that book again, right? That's the temporal locality. And then you may have some books in the desk. Usually books that may be needed soon can be in your desk. Some of them are in the bookshelf. You don't need them as much. Some of them are at boxes at home. You really don't need them that much. And some of them are boxes in storage. And those are less needed. So basically, recently used books tend to stay on desk. Maybe your computer architecture books, if you're reading them, or books for the classes you're currently taking, right? Until the desk gets full, of course, right? Well, your hand, you can keep only a couple of books, probably. One book is a good start. Book level parallelism is also good. But your hand is kind of like the register file. You're operating on this book at this point, right? And then your desk is like the caches. Okay, you drop this book, you switch to another class, and then you read those books. And then because your desk has limited capacity and you don't want to fill it with books only, because you may want to have some drinks also, right? As a result, you basically move some of the books to the bookshelf, right? So this is the temporal locality principle, right? And the size is going to matter also in this case, because at some point this cache is going to get full, and we're going to ask the question, what are we going to replace from this thing, right? Okay, the spatial locality principle is interesting also. For example, you can organize your books such that there's some logical principle in the organization. All books related to computer architecture may be spatially in the same location in your bookshelf, right? So whenever you go to your bookshelf, computer architecture, it's here, and sequentially you can figure out which book you want. That's the spatial locality. That's how you can improve spatial locality. Things that you're going to access close by, you put them together. This is called data mapping. You're mapping your data to close by locations. Whereas if you mapped your data randomly, computer architecture book 1 goes to this side of the bookshelf, computer architecture book 2 goes to this side of the bookshelf, computer architecture book 3 goes to that side of the bookshelf. Good luck accessing that data easily, right? This is latency. You have to go through there, assuming you're going to access those things, let's say, around the same time, right? So basically, if you organize and categorize your books well in the shelf, you can actually exploit spatial locality much better, right? Okay, hopefully this is interesting. You can make a lot of other analogies, but we don't have time to make a lot of other analogies. Any questions? Otherwise, I'm going to go into a little bit more detail. We're going to build this cache soon. So let's talk about caching in the pipeline design. Okay, I don't see any hands. So it turns out the cache needs to be tightly integrated into the pipeline. So ideally, for example, remember when we designed pipelining, we said there's instruction memory, there's data memory, and we assumed one cycle access. Right? That was the assumption. Now we're going to make the assumption a little bit more realistic. Basically, if you want to supply that, there needs to be a cache that gives you data in one cycle. Fine, you can build it, no problem. The problem is going to be small, right? So if you have a high frequency pipeline, you cannot make the cache large, but you ideally want a large cache in a pipeline design. Right? It just doesn't work. If you want to access the cache with one cycle, only in one cycle, you need to make that cache small. This is another reason why we have a hierarchy, basically. Instead of having just one level 1 cache, we have a level 2 cache. Level 1 cache can be one cycle to satisfy the needs of the pipeline. But level 2 cache can be longer access latency, except the processor needs to stall to access the level 2 cache, or you need to do out-of-order execution to tolerate the latencies that happen in the level 2 cache. Okay, so the key takeaway is level 1 cache is really part of the processor, if you think about it. Meaning, the processor, it's really dictated. The design choices that you make in the processor dictate how large and what structure, how large the level 1 cache can be and what structure it can have. So ideally one cycle, but we're going to see caches that are 3 cycles, etc. So, okay, there's another note, which is manual. Who manages the cache? Programmer or hardware? In general, when we talk about cache, it's a hardware cache today. It's kind of the assumption in general, but that's how I kind of defined it also, right? Automatically managed based on the hardware. Software can also manage it. But manual means programmer manages data movement across levels of the cache hierarchy. This still exists actually in GPUs. I'm going to show you very quickly. But usually it's too painful for programmers, especially on substantial programs. Because now the programmer gets exposed to this hierarchy and they have to decide, oh, where do I put the data in this hierarchy? Right. And it used to be that way, especially in embedded processors, but GPUs also start introducing caches. A lot of ML accelerators, machine learning accelerators also still do scratchpad type of memories. This is also called a scratchpad memory. Manual management of the caches, scratchpad memory, because it's visible to the programmer now. So it has its own address space that needs to be dealt with. Automatic means hardware manages the data movement across levels transparently to the programmer. Programmer doesn't need to do anything. Of course, this is the huge advantage that programmer's life is easier, right? Which is important, as we have discussed in the past, right? And the average programmer doesn't need to know about caches. So for example, you don't need to know how big the cache is and how it works to write a correct program. But the issue is a little bit different if you want a fast program. If you want a really fast program, you still need to know what your cache hierarchy looks like, because you may design your program such that locality is terrible, right? If you're not careful. If you don't know the sizes of the caches, for example, and how they work, you may design a program with terrible locality in general. So if you want to optimize your program, this is still very important. And given that a lot of the programs today are bound by memory access latency, it's really important to optimize your programs. We're going to see an example of this next lecture. But just to give you an example, GPUs do it both ways. A lot of modern general purpose processors, CPUs, they have caches that are not visible to the programmers. Whereas GPUs, they started with scratchpads, meaning programmer manages the caches. But over time, they said, okay, this is too difficult. As they became more and more general purpose, they said basically, okay, programmer can also use these as caches, meaning programmer doesn't want to deal with the management, so hardware manages it. So they have kind of both ways, right? As you can see over here, this in this particular NVIDIA Ampere GPU, 192 kilobytes per streaming multiprocessor can be used as L1 cache and or scratchpad, or some sort of combination, basically. And this is increasing. The size of this is increasing. And again, you can see another example from Hopper here. Okay. So if you look at ML accelerators, we've seen examples before. Here, there are no caches currently. If you look at the tile that we examined in the past, this is a SIMD processor, if you remember. It has a SIMD floating point multiply and accumulate units. And basically, in each tile, you have a 42 kilobyte scratchpad cache, totaling 18 gigabytes in the full chip in this particular example. So basically, here the programmer does everything, or the compiler. So this is why this is a bit more difficult to program. Okay, and then this is increasing over time. Let me just give you an example of the old things before we go into caches, because in the old times, there was caches also. The memory technology was a bit different. So you can see this is a technology that you don't want to carry in your pocket, right? This is the main memory technology in the 1950s, 1960s. There's a lot of magnetic things. Then it became, this is drum memory because of its operational principles. And then it became core memory. And if you look over here, even the structure is very similar, right? Yes, there's magnets. The magnets need to move, and depending on the orientation of the magnets, you store 1 or 0. But you still have the word line and bit line two-dimensional array structure. It's just not electronic in this particular case. And I like reading this over here very quickly. So using smaller cores and wires, the memory density of the core slowly increased. And by the late 1960s, the density of about 32 kilobits per cubic foot, about 0.9 kilobits per liter, was typical. However, reaching this density required extremely careful manufacture, which is still a problem, actually, which was almost always carried out by hand in spite of repeated major efforts to automate the process. A lot of things that happen by hand to make the DRAM work also today. The cost declined over this period from about $1 per bit to about 1 cent per bit. That's extremely expensive by today's standards, if you remember the numbers. We're talking about main memory. DRAM is like $0.03 per kilobits, maybe even lower today, actually. The introduction of the first semiconductor memory chips in the late 1960s, which initially created static random access memory, SRAM, we have seen, began to erode the market for core memory, this thing over here. And the first successful dynamic random access memory, DRAM, the Intel 1103, followed in 1970. Its availability in quantity at 1 cent per bit marked the beginning of the end for core memory. So that's how DRAM actually replaced these huge things, because it was easier to manufacture, and also it was cheaper, as you can see. And today it's much cheaper. And this is all of that improvements in the memory technology. The cost per bit enabled where we are today, basically. I don't think AI, for example, would be possible without those improvements. There's, of course, a lot of other things that went into AI, but hardware, both GPUs and memory, are a big part. In fact, memory is still a huge part of it. Okay, so automatic management. Let's talk about this automatic management. I've already mentioned this, what Wilk said over here, but let's see it a little bit more. By this slave memory, which is called cache memory today, I mean one which can automatically accumulate to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. So you've seen this before. There are actually earlier cache papers that I'm not going to talk about, but caching is done much earlier. And this is an example that we may return to. We're going to look at how the cache is organized, but this is a paper from 1960. And you can see there is a tag store and there's a data store. I'll introduce these concepts a little bit more later, and we're going to actually build a cache. But data store is where the data is stored. You bring the data from main memory, you store it in the data store. Tag store is an index into the cache that tells you which memory address that data belongs to. So you need both of these. You need the tag, which is part of the address, which basically identifies the address that this data belongs to, and you need the data. So you can also think of tag as a metadata that specifies where the data comes from main memory, right? Okay, so this is the modern memory hierarchy. Again, I've shown you a lot of examples of this. I'm not going to go through this in detail, but I will mention that later in the last lecture probably. So there's a register file which is managed by manually or compiler, and then there's a huge memory hierarchy that's managed automatically. And then there's a part, DRAM and storage, swap disk, which is part of the storage, that's also managed by the system. It could be the programmer or the system. We're going to talk about the virtual memory system. I mentioned that briefly last time, but we're going to go into a little bit more detail. So this is also automatically managed in a different way. But we're going to see that, and that's part of the memory hierarchy as well. Okay, let's do some latency analysis. And probably by the end of that, we're going to finish this lecture. This is going to be a little bit fun. But basically, it's going to also show different design decisions, and the cache can actually lead to different latencies or similar latencies. So let's assume that you have a given memory hierarchy level I. It could be level 1 cache. Has an intrinsic access time of Ti. Basically, you have some array structure, tag and data, and it takes time Ti or T1 to access that array structure. That's in isolation, how long it takes to access this cache, called Ti. It also has a perceived access time, large Ti, that's longer than Ti, because whenever you access the cache, if the data is there, the access experiences small T1 latency, small Ti latency. But if the data is not there, then you need to go to the next level. That's why this is called the hierarchical analysis. And in unison, how long on average it takes to get the data from a level is the perceived access time. The data may be in the cache, may not be in the cache, and there's some probability associated with each of those. Okay, so basically, except for the outermost hierarchy level where all of the data resides, when you're looking for a given address, the processor needs to access address X because of a load or store. It supplies the address X to the first level of the cache, and there's a chance at any of the levels, except for the farthest level, which is storing all the data, hopefully, there's a chance that you're going to hit in the cache, meaning the data is actually in the cache. The data that you're looking for is in the cache. Address X is in the cache. The tag store says, I have address X, and here it is. This is called the cache hit. And in this case, the access time is this intrinsic access time of that level, Ti, T1, okay? And then there's a chance that you're going to miss in the cache. This is called a miss rate, MI, of that level. And now your access time is going to be small Ti at that level, T1, assuming this is level 1, because you need to access the cache to figure out whether it's a hit or miss. And if it's a miss in this particular case, you're going to access the next level, which is the large Ti plus 1, which is basically the access latency of the remaining part, the perceived access latency of the remaining levels. Okay, so hopefully this is clear. This is a hierarchical thing that we will actually look at. But basically for any given level, the hit rate plus miss rate is equal to 100%. You have 100 accesses, 99 of them are going to hit in the cache, one of them is going to miss. Right? That's one example. Hopefully that's clear. Okay, so basically this is a hierarchical latency equation. So if you look at this Ti, large Ti, perceived access time of level I is a hit rate of level I times time it takes to access data from level I, little Ti, plus miss rate of level I times, in parentheses, time it takes to determine that there is a miss, which is the same as time it takes to access level I, plus the perceived access time of the next level, right? You can also write this as, because Hi plus Mi is equal to 1, this perceived access time of level I is the access time of level I of the array, plus the miss rate from level I times the perceived access time of the next level. Okay, that's the hierarchy. Now we're going to examine a real example. So HI and MI are defined to be the hit rate and miss rate of only the references that miss at that level, basically, I-1. Yeah. Okay. So this is the recursive latency equation that I showed you earlier. So what do you want to do here, right? Basically, the goal is to achieve desired perceived access time within allowed cost, T1, basically. T1 is the perceived access time that from the perspective of the processor. It's level 1 cache. Ideally, you want this to be 1 cycle, right? But maybe it's not possible. Ideally, in all levels, you want the perceived access time to be equal to the array access time, especially at the top level, right? So to be able to do this, what can you do? You can keep the miss rate low. That's good. Or you can keep the access latency of the perceived access time of the next level low. So keeping the miss rate low, you can increase the capacity. This lowers the miss rate, but it can increase the access time of the array because bigger is slower, right? Or you can lower the miss rate by smarter cache management, which we're going to talk about. Replacement, you anticipate what you don't need and throw it out. You prefetch, you anticipate what you need and bring it in. We're going to talk about those later after we build the cache tomorrow. Or you can keep the perceived access latency of the next level low. This enables faster outer hierarchy levels, but again, cost may increase over here. Or you can introduce intermediate hierarchy levels at the compromise. Basically, this is why we have the hierarchies that we have, because there is no easy way of building a fast cache that's also large. So you actually progressively increase the cache size to minimize the perceived access latency of each level. Okay, let's look at an example. We're going to look at a real example from Intel Pentium 4. It's at an L1 data cache of 16 kilobytes. Forget about 8-way right now. It's associativity. You'll see it tomorrow. And then it's at an L2 cache of 1 megabyte. And it has some access latencies. And this is the L2 cache. This is the real Pentium 4. We're going to do this latency analysis quickly. It's 3.6 gigahertz. It was one of the fastest processors of its time. So L1 data cache capacity is 16 kilobytes. Intrinsic access latency happened to be 4 cycles, not 1 cycle, because it had heavy out-of-order execution to tolerate long latencies. L2 data cache capacity was larger, but intrinsic access latency of that level, T2, small T2, is 18 cycles. And then intrinsic access latency of memory, we're going to assume it's 50 nanoseconds, 180 cycles. It's actually small compared to Pentium 4, but that's what we're going to assume. So remember this equation. So if you plug in some miss rates, let's assume that the miss rate at level 1 cache is 0.1, meaning 10%. 90% of the access is hit at level 1. And then the 10% miss in level 1, and you go to level 2 for that 10%. And 90% of that 10% hits in level 2, but 10% of that 10% misses in level 2, so you go to memory. So if you do this hierarchical latency equation, this is what you would get. If we had time, I would compute it, but I'll let you compute it because we don't have a lot of time. But basically, the perceived access latency of level 1 is 7.6 cycles, which is pretty long. Perceived access latency of level 2 is 36 cycles, if you do all of the equations that I said. Even with a 90% hit rate, 90% is a lot of hit rate, high hit rate. 90% of the time, the data you're looking for is in the level 1 cache. And if you miss 90% of the time, the data you're looking for is in the level 2 cache. Now let's take a look at 99% hit rate, 1% miss rate. If you do 1% miss rate in both of those cache levels, perceived access latency of level 1 becomes 4.2, which is much nicer, closer to 4, as you can see. And the perceived access latency of level 2 becomes 19.8. Okay? What really matters is perceived access latency of level 1, because that's what the processor sees, right? Processor is directly connected to level 1. Now, there's another way of getting closer to, let's say, 4. And this is if the miss rate of the first level is 95%, 5%, hit rate is 95%. And if the miss rate of the second level is 1%, this is what you get. Perceived access latency is 5 cycles on level 1. Now let's take a look at a different version of this. This is actually interesting. If the miss rate of level 1 is 1%, you hit 99%. But your level 2 is not very effective, let's say. Miss rate is 50%. Hit rate is 50%. Basically, it's kind of half of the access is hit in this level 2 cache. Your perceived access latency is very similar in these two cases, which is very interesting. The reason is here, you're getting a very high hit rate in the fast cache and an even higher hit rate in the slow cache. So you're going to memory not very often. Here you're getting a very high hit rate in the level 1 cache, but very high miss rate in the second cache. So you're going to memory equally more often. In the end, this balances out. You get about 5 cycles the perceived access latency from the processor. So there are different ways of designing the cache to get, the takeaway is there are different ways of designing the cache to get a similar access latency from the processor's perspective. Okay, this brings us to a very nice place to finish off. Tomorrow, we're going to start with how these caches actually operate, and we're going to build up to how to optimize the performance of caches. And then next week, we're going to start doing things like prefetching or more advanced caching. Sounds good? Okay, I'll see you all tomorrow. Have a good rest of your day.